Welcome back. We're going to study astronomy starting today, and we're going to look at the different ways that electromagnetic radiation can strike the Earth. So different forms of energy waves that come from stars and different objects, distant objects. So we'll look at light, we'll look at microwaves and infrared and X-rays and all the different things that maybe it was possible that you didn't know were actually really one thing, which is simply an energetic wave. We'll look at that. We'll look at telescopes and how that we've been able to view these objects, and the basically our very first toe in the water in terms of learning about the universe around us. So let's look at some details. Stars are essentially nuclear furnaces, and they're sending out ridiculous amounts of energy. And this energy is in the form of light. You can see a star. It's also in other forms of energy. So energy is not just light. Heat is a form of energy. Microwaves are a form of energy. In fact, all of the various types of energy that we know are in a spectrum that really the only difference is the amount of vibrations, or how many vibrations in a second each of these forms of energy takes. So whether something is an X-ray or a radio wave or a light wave or a heat wave, all of these essentially is the same type. It's just different speeds of the energy moving through space. This is called the electromagnetic spectrum, and you'll see that nothing has to be there for these waves to go through. It can travel through complete empty space. You have an electricity, or you have electric field, and you have a magnetic field working synchronized so that they are both helping each other through empty space. It's pretty cool, actually. So the spectrum is not just light. Light is only a very small part of the electromagnetic spectrum. So the longest waves, the ones that have the lowest energy, are radio and television waves. Then above that, as they get smaller and more energetic, then they will be microwaves. Now, microwaves cannot just warm your coffee. It can also, it's the microwave towers that cell phones work on. Then anything faster than that is no longer considered a microwave. It's actually infrared, which is heat. So you can actually feel that. You've got nerve centers in your hands that can feel heat. That is a form of electromagnetic radiation. Visible light is now picked up by the retina of your eye. You can only see in that very, very small section. So you can imagine that there are other animals. There are insects that can see higher, so they can see in the ultraviolet range, where we are blind in that range, but there are insects and other animals that can see in that range. If you were to speed it up still, you get X-rays, which is powerful enough to penetrate soft tissue but gets stopped by bones. That's why you can take pictures of your skeleton with X-rays. And then as it speeds up further, you are into the gamma radiation, which is emitted by radioactive material. There's even a further one than that called a cosmic waves that's even higher energy than gamma. So if you're looking at the form that all of these have in common is that they have a frequency and a wavelength. The wavelength is simply the distance in meters between the crests of two adjacent waves, or the troughs of two adjacent waves. And as you get more wiggles per unit of time, you have a higher frequency. So that's called the frequency of that wave. And the frequency is how you would determine whether something is an infrared or a visible light or a microwave, etc. Now, telescopes historically are light telescopes. They are picking up just the vibrations of light in the electromagnetic spectrum, and so you can see any light that's reflected off of an object. So you can look far away in an eyeglass and see a ship approaching. Well, you're looking at the light that's bouncing off that ship that's coming in front of that ship. That's how you can see something, as you're looking at its light. You can also look at the light from a star. You can look at the light from anything that emits light. So that's a light telescope. There's two types of light telescopes. The first one is refracting, and refracting means bending. And so light will bend when it comes through a medium thicker than something else. So, for instance, light going through a vacuum, as soon as it gets into the atmosphere of the Earth, it slightly bends because the atmosphere is thicker than the vacuum is. If it were to go into something like water or glass or plastic, for instance, lenses, it would even bend more. So this bending of light, you can play with it in such a way that you can make that light focus onto the back of your eye, and you can see it very clearly. So a telescope helps you very clearly magnify something that's far away, the light of which is not hitting the back of your eye well enough for you to see it in detail. A different type of telescope, and one that you can actually make it a little, you can go farther with a reflecting telescope, because it's easier to make a mirror bigger than a lens. A lens is a very specific curvature of thick glass, and a mirror, you can make a curvature of a thinner piece of glass, or even multitudes of little pieces of glass kind of together, and get a reflection off of that. And then that mirror can then essentially focus that image through a small lens and into the back of your eye. So you can get a very large reflecting telescope for not a lot of money, compared to a very large refracting telescope, which would cost a fortune. Now, you don't have to have visible light in order to have a telescope. Telescope just means seeing at a distance. That's what telescope means. And so you can look at the wavelengths in any of these spectra. You can look at them in X-rays. You can look at them in infrared. You can look at them in microwaves. You can look at them in radio. So you have radio telescope observatories. You have microwave observatories. You have X-ray observatories. I don't think you can look in gamma. Maybe not. Maybe I'm wrong. But I know you can look in these other lower energy spectra. So you can still call it a telescope. Now, there are, in terms of astronomy, from the 1990s, the Hubble Space Telescope was launched. And because there's no, it's out in space where there's no atmosphere, there's no distortion caused by the atmosphere, and you can take much better pictures of deep space objects. And so in terms of knowing what has been out there, we know as a people way more now since 1990 than we ever knew before in terms of galaxy and different kinds of nebula and all kinds of different structures and that are out in deep space as a result of our telescope. We've also launched spacecraft. There's spacecraft all over the solar system, going towards the sun, going away from the sun, going all the way to the outer edges of the solar system. We have spacecraft that were intended to take pictures of the planets in the outer solar system that have gone out of the solar system and are still not completely dead yet, that are still sending back information from past our solar system. So all have names, all in different mostly by NASA in the United States and the different space agencies worldwide. We've also landed on the moon, which is our satellite. That's our closest satellite to us from 1969 onward, and we've gotten tons of information as a result of that. The technology that we used in order to get to space has totally paid off in terms of making our life better. Everything from Tang, anybody that's ever drank Tang, which is kind of powdered orange drink, which is gross, to Temper mattresses, to heart valves, all of this is a spin-off of the investment that we as a country put in our space system.